صباح الخير زينب مع خالد.
صباح النور دكتور.
Can you see the شباب؟
Yes.
Okay. وصلنا طبعا إلى هاي النقطة أو this slide. In the previous lectures I have covered يعني ال types of circuit breakers, their classifications, their principle of operation on quench to quench arcs. And today, inshallah, I'll try to give you the electrical specifications based on the standards for circuit breakers. And with some examples, inshallah, things will get clearer, okay, on how to choose a circuit breakers. This slide shows you the sequence of fault clearing, okay, from the initiation of a fault. At this moment, a fault happens. Okay, when a fault happens, current will increase, and that current will increase both AC and DC components. And so after some time, the relay, let's say time, which is the relay operating time at this moment, the current decaying DC will decrease to some degree, but the relay, the current will have both AC and DC, but the relay will take actions within a short time. Now it depends on the relay time. Some relay take 1 cycle, some relay take 2 cycles, okay, to detect the faults and give a command to circuit breakers. In the standard, they assume the fastest. So in this case, they have assumed 0.5 cycles of relay operating time from this fault initiation to the point where an action is given by a relay. So this is the based on timing based on the standard. Okay. So after half a cycle, half a cycle, the relay now, the circuit breaker trip coil is energized. Now it's received the command from a relay and it's get energized to trip its contacts. So from this moment till the contacts that I have mentioned, there are primary contacts and arcing contacts. Once the contacts are physically open, okay, this is called the mechanical time of the circuit breaker. So at this moment, the currents still has a decaying DC, depends on the circuit breaker operating time, okay, and so as per the standard, the circuit breaker rating has to be chosen at this time, exactly at this time, okay. So its ability to break current, short circuit current here is not when it's fully clear the arc, okay, it's here. So this is an important point that you have to know, and we call this time from the initiation of the fault to that point, we call it contact parting time, right? So we always rate circuit breakers when they open during faults. We call it we should rate them based on their contact parting time, at the contact parting time. And there is another rating. We should also rate circuit breaker when they close onto false. Suppose I have a false and I ordered uh, once a relay opens and give a comment at this point, the current is too high, and we rate them. We call them this it's close and latch rating or peak rating, okay? Because it has the highest amount of DC and the current is big. So this is one important information or ratings for the circuit breaker is ability to close on high current during the instant of receiving a command from a circuit breaker, from a relay. Now, after a relay physically start opening its contacts, there will be an arc initiated between the contacts and takes time until it's fully extinguished using the techniques I have mentioned before. So the arcing time depends on is there any zero crossing in the current so this time, so it could take from 0.5 to 0.75 cycles for breakers to extinguish, and for some other breakers could take even longer than it could take even 2 cycles just for arcing. Okay, so the total time from the fault initiation to until you remove all the arc by the circuit breaker is called the fault clearing time, where the faults is fully cleared by all the bolts. Yani not only the faulty phase, all the bolts has been because in circuit breaker, some for single phase, for 3-phase system where you have one breaker in each phase, the breakers, some of them, they will open before the others, okay? Depends on the, because let's say vacuum, they operate when at zero crossing, at when currents cross zero. So it makes some phases will have operate before the others. So these are the neat things. The important steps I want you to remember from this slides is the contact parting time is different than fault clearing time. We have also mechanical operating time, which is the physical time for a circuit breaker that it requires to open its contact physically. And the time that extinguish the arc is the arcing time. The total time of the mechanical operating time we call circuit breaker interrupting time. Okay. So these are the so we always now in calculations we would like to know what's the contact parting time. Okay. And we can also find what's the maximum current during the at this moment when the circuit breaker started at the peak value of at the initial peak value of the current. Let's go to the standard now. How the standard defined the ratings, I will show inshallah later. We have a nominal. Let me take. So you have a nominal operating conditions. So nominal operating or normal operating conditions. Sorry, it's the all circuit breaker are rated at specific temperature and specific altitude. Now, most like as per IEEE standard, they defined the ambient temperature from minus 25 to 40 degree, and for IEEE minus 40 to 40. and the altitude is less than 1000. So suppose the breaker is rated 10 kiloampere breaking capacity, or rated current is 100 ampere or 1000 ampere. This is valid at this temperature and this altitude, up to this altitude. If you have exceeded this temperature or exceeded this altitude, there will be a derating. Okay. So now this is the altitude, for example, it's 1000. So the rating will be same as 1 per unit. When the temperature is, let's say now at 40 degree, this is 40 degree, the first case 40 degree. So one means there is no correction factor, there is no derating. If you use the breaker at lower temperature, let's say at 20 degree instead of 40, and design at 40, you can even it can take more current. So in this case, it can take 15% higher than its rating, because it is not at its maximum temperature. Similarly, if the temperature is higher than 40 degree, it will be a reduction in its rating if it's exceed 40 degree. Now, if altitude more than 1000, let's say 1200, so, and the temperature is 40, there will be a decrease by, let's say, uh, suppose here your altitude 3000, so roughly 5% has reduced from its rating. So this is one factor you need to consider. So if the temperature or altitude is higher than the maximum values here specified by standards. Rated frequency, we have 50 and 60 hertz. Some breakers that are rated for 50, some rated for 60, some rated are 50 or 60. So let's say why this is important sometimes in the frequency, because if the frequency, if it's you are rated and at 60 hertz or 50 hertz and use it for a system at lower frequency than the rated value, then the zero crossing, it will, at lower frequency, zero crossings will be slower, more time between each zero crossing. So that will delay the breaker operating. So that's why we'll have longer arcing time for this. So some manufacturers, they already specifies this is for both frequency 50 and 60. There is no concern in this case, and you have to look to this if you want to use a breaker for non-standard frequency values. The rated maximum operating voltage, which they specified, means the maximum voltage that you can use for this breakers, and means your operating voltage of the system has to be always not exceeding this voltage. You can use a breaker of higher voltage for a lower voltage system, but you cannot use it for a voltage higher than its specified maximum operating voltage. Rated continuous current, IR or I rated, it's the maximum RMS current that the circuit breaker able to carry continuously under normal operating condition that I have specified, the rated temperature, altitude below 1000 and so forth. Okay. So it is in general will not use a circuit breaker for a load. Now we should compare full load currents with this value. So our continuous current rating has to be greater than your continuous maximum full load current. Okay. As per IEEE IEC sorry standards, the rated currents عادة يجون not every ampere, like they are a standard value, like 630, 800. You don't have, let's say, 550. They have 1,600. And you say the value between these each two is a factor of 1.25. Let's say you multiply 1.25. Roughly, this is a series of 10 to the power n over 10. So if you multiply this by 1, you give you this. By 1.25, you get this. 1.25, you give this. So it's in a steps of 1.25 or roughly. Okay. This is the standard ratings of circuit breakers. There is also in the specification something called rated short circuit breaking current. This is what I was trying to mention. Now, during the starting current, during the short circuit current goes too high, and this is called the peak value of the short circuit current. Then try to decrease as the decaying DC decreases. When at the contact parting time here, the current still has a DC value plus the AC components. So the total current that a circuit breaker should be designed to break is the DC square plus RMS value square under the root of the AC components. Let's give you total asymmetrical current that the circuit breaker should be able to interrupt. While after maybe arcing time, then the current will be, or circuit breaker will fully clear the faults. So this is here where we want to clear. Now, as per standard, nowadays, they have not defined the total. The older standard, they used to rate the breaker for its ability to break short circuit current based on the total current. Now, they give you only the circuit breaker manufacturer, because they are following the standards, they will give you the short circuit breaking capability of the circuit breakers. They give you the AC components only at the contact parting time, and the manufacturer have already included its ability to uh, uh, to 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 also uh, to include a portion of a decaying DC. So here, when a circuit breaker rated short circuit breaking current rating is the highest short circuit current. So always you will compare this value with the maximum steady state, probably short circuit current. The highest short circuit current in RMS that can be interrupted by circuit breaker at the instant of primary contact arcing parting time. Primary arcing contact separation, and under the prescribed standard condition, like in temperature, attitude, and okay. Or sometimes at rated voltage and standard operating duty. I'll give you this later, inshallah. So rated short circuit current is characterized by two values: is the RMS value of the AC component, which is the steady state AC component value, and the DC components, which is the DC value, which is at the contact parting time. This is the DC value. At the peak value also here, it has both DC and AC components. If the DC component is less than 20% of the AC component, we consider this like almost at steady state. And then in that situation, the circuit breaker will be rated based on only AC components, okay? Because DC component is negligible, so when it's less than 20%. And this is according to IEC standard. According to the same terminology, they don't call this rated short circuit breaking capacity. They call it require symmetrical interrupting capability. Symmetrical means it means the AC components of the fault current. So it's the value of the symmetrical component of the short circuit current in RMS value at instant of arcing, يعني instant of contact separation, that the circuit breaker shall be required to interrupt at the specified operating voltage on the standard operating duty cycle with DC component less than 20%. So this looks like only they consider the AC components now, because they are talking about symmetrical breaking capacity. This is short circuit current capability of the circuit breaker to break that AC component. And now the breaking capacity, the interrupting capacity of circuit has to be greater than maximum short circuit current, symmetrical short circuit current. And similarly here, you should choose a breaker such that this value is higher than the maximum short circuit current. So this is according to both IEEE and IEC. So this terminology is same equivalent to in IEC they call it short circuit breaking current, and here they call it symmetrical interrupting capability or breaking capability. The breaking capacity is according, also it has a standard value from 12.5K, 16K, 20K, also a factor of 1.25. And this series called, the series is famous and adopted by the IEC. This is not, you don't have to memorize or this. The another standard they specify, especially in older standards, the required asymmetrical current interrupting rating. So this is like I total breaking capacity, which represent the total RMS value that includes both AC and DC components, okay, at the contact separation time, which is at contact parting time. While the other specified, these two does not include the DC components on those specified values. Here it's including the DC components. So at what, but the DC component varies with respect to time. Okay, as longer time, the current DC decays more. So the standard defined that the time constant of DC is 45 milliseconds, which is this is the DC, which is e to the power minus t over tau times 100, which is to make it in terms of 100%. So it decays, and tau is x over r ratio of the circuits. And so it depends on this now. A standard they specify x to r ratio L over r. L over r is 40 millipixel, and if you take the corresponding value for 60 Hz, this is 17. X to r is 17. So they specified the standard value of 45 for the manufacturers, and they assumed an operating time for relay of both 0.5 cycles in their specifications. So like the contact parting time is 0.5 cycle plus the circuit breaker mechanical time, and that gives you the contacts separation time or contact parting time. So 45 milliseconds correspond to 17 x to r ratio, or for 60 Hz, or 14 for 50 Hz. And if you would like to relate uh, the symmetrical, we call this sometimes the asymmetrical. So I asymmetrical is a function of symmetrical current, which is the symmetrical short circuit current by this factor. So this is called sometimes in old standard the S factor, 1 plus 2 times. There, I'll show you derivation. Where does this come from? Inshallah later. Um, so if the short circuit current, okay, lower than the symmetrical component by 80%, then you can always specify that the circuit breaker will fulfill the it will be able to break a current even at higher time constant. Okay. Inshallah, in the examples, I will show you this. This is the IEC. They in IEEE they specified 45 milliseconds, but in IEC they specified also other value. This is the standard values. This is now the elapsed time, means the interrupting time, the contact parting time from the relay time plus the circuit breaker mechanical operating time. So at 45 millisecond, the DC will decay to let's say to for 35%, okay, of its value. So this is like the decaying DC. How do you evaluate it in terms of percentage? Uh, on IEC, they specified other values: 120 milliseconds, 75 for circuit breaker rated less than 52 kV. They use 120 milliseconds. For more than 550, they go 75 millisecond and so forth. But both IEC and IEEE, they specified most of their breakers at 45 milliseconds. Um, now, how the how do we know now the contact parting time? If the circuit breaker rate, most of the manufacturers will give you circuit breaker total interrupting time, which is from the relay from the relay from the coil circuit breaker energize. Once a relay receives send a command to a circuit breaker, from this moment to fault clearing time. So they give you the manufacturer give you this one cycle circuit breaker, two cycle circuit breaker, three cycle circuit breaker, or five cycle or eight cycle circuit breakers. So this is means total clearing time. It doesn't mean the contact parting time. So what they did, the standard, they said for 8 cycle circuit breaker, their contact parting time is 4 cycles, and for 5 cycle it is 3 cycle for contact parting time. For 3 cycle it is 2 cycle, like 1 cycle for arcing almost, and for 2 cycle, there is half cycle, 1.5 cycle contact parting time, and half cycle, for example, for the arcing time. And also for 1 cycle, they use 1 cycle uh, contact parting time, and the circuit breaker total clearing time is same. And the X to R ratio, now if I have this time, okay, which is contact parting time, and I can evaluate now the DC value, the S factor, which is S factor is this. This is the S factor, this factor. So they give S factor for, let's say, of the contact parting time is 40 milliseconds, for example, and the X to R ratio is 17. Okay, then this will be 1.1, means this factor will be 1.1, means the asymmetrical current will be 10% higher than the symmetrical current. There is other factors, other also specifications. It's called the peak current rating, or the making, they call it peak closing or peak making current rating. So this, or like sometimes they call close and latch rating. So it means the peak value. This is the value I have mentioned here. This is the specified here, this value. The maximum peak value, the circuit breaker is able to withstand when it's closed into false, when tried to open also false. And its value can be calculated using this for as bare standards. The peak value can be calculated from this formula. I will drive this for you later. But now if we substitute, already tau we said it is 45 millisecond as per standards, and time now is the we assume now from this moment of an initial fault to a relay operating time is 0.5 cycle, where it reached the peak maximum within half a cycle. When you substitute here half cycle in this half cycle, which is, let's say, for 50 Hz will be 0.5, 10 milliseconds over 45 milliseconds, and you substitute here times root 2, it will be a factor of 2.5. For 60 Hz, the half cycle time is 16 millisecond over 16 point something milliseconds over 16.6 will be 8.3 millisecond for the relay operating time. At this standard DC time constant, you'll get a peak of 2.6. For other applications that have higher time constant, they use 2.7 to get the peak from the symmetrical current, fault current. For the short, there is also something called short time current rating. Short time current rating is the maximum short circuit current in RMS value that the circuit breaker can interrupt without tripping for a specified period of time. Yani, circuit breaker manufacturer tell you this breaker can handle this current for a duration of 1 second or 2 seconds or 3 seconds. This is called short time current rating. So this is very important if you want to know how long the fault can persist, okay, so that the circuit breaker will be able to to handle this high current for this duration. So sometimes I don't want to trip a breaker. I want to use it as a backup, so it should handle this current. I don't want to instantly trip it. So it should handle the heating from the short circuit current for a duration of minimum specified. This is called short time current rating. There is also rated dielectric strength. Rated dielectric strength here is related to the voltage now. The medium we used, like as vacuum or air circuit breaker or SF6, they have a dielectric strength. If you see that dielectric, the breaker will get damaged. So we have different specification for the voltage withstand of the circuit breaker. So we have 3 terminologies: rated power frequency withstand voltage. This is not the operating voltage. This is the maximum voltage that the circuit breaker, for example, handles within 1 minute, the highest voltage at the power frequency at 50 hertz, for example. And sometimes also here, this is so during over voltage, during switching, sometimes the voltage will go high, but this is the rating for 1 minute. Highest voltage it can handle within 1 minute only. There is also rated lightning impulse withstand voltage. That is the maximum voltage peak that the circuit breaker will handle during, let's say, a lightning strike. Also, there is a switching impulse withstand voltage. And this is applicable for circuit breaker higher than 300 kV, and they use this waveform to test. I'll show you these waveforms. This is the lightning impulse voltage. They did test this circuit breaker. It has the voltage will increase within 1.2 microsecond to its peak, and then decays down within 50 microseconds to half of its peak. So this is called 1.22 to 50 microsecond standard impulse waveform. So the manufacturer will test, they tell you what is the maximum lightning impulse they have tested. They have also the switching, it has 250 until it reaches peak, 250 microsecond and 2500 microseconds or 2.5 milliseconds until it decays to its 50% of its maximum value. And the standard, they specified this for manufacturers so that they will test their breaker at those standard specifications. This is like an example from IEEE standards for voltage for AC generator circuit breaker. They call rated insulated level. For voltage circuit breaker less than 7.2 kV, this is the rated power frequency withstand voltage. And this is the lightning impulse withstand voltage. So any manufacturer of manufacturing a circuit breaker of up to 77.2 kV, they will specify this circuit breaker already tested up to 20 kV of RMS voltage and 60 of peak voltage. Okay, so that can withstand a lightning up to this. And similarly for higher IEC standard, they specified also the voltage this is the operating voltage, and this is the power frequency voltage, and this is the lightning impulse voltage, and similarly for other voltages. Rated transient recovery voltage, it relates the ability of the breaker to the ability of the insulating now medium to recover its insulation properties after current interruptions. Now, to test this, they have also standard specified two standard waveforms. This is mostly used for one-time constants like this. So this is the actual voltage. This is transient recovery. Once you open a circuit breaker, the voltage at between contacts of circuit breaker will increase in a specific pattern. So when that voltage increases faster than the dielectric recovery, then the arc will not be extinguished. So that's why also the standard specify that this manufacturer of circuit breaker should also test their breakers with either of these two waveforms. This is normally used for the 4 parameters used for circuit breaker rated more 100 kV, and this is 2 parameters, which is this is the 2 parameters waveform used for circuit breaker rated less than 200 kV, less than 100 kV. I'll try to. There's also one specifications for the capacitive switching. Capacitive switching is it affects the voltage that will develop across the contacts. Suppose we have a capacitor. You want to switch a capacitor bank, or you want to switch unloaded line or unloaded cable. Okay. So we will model like there will be a shunt capacitance that represent the cable or the line, and this is the source. Now, suppose now, this is the voltage when this was closed. Suppose this is closed, there is no load. What will be the voltage across the shunt capacitance, Shabab? So this is the model for this. When you close the breaker, what will be the voltage here? It almost same as the voltage supply. Okay, so it will be same as this blue line. And what will be the current during when this is closed? It will be very small current, which is the charging current. Okay, so obviously when you open the breaker, the breaking capacity is very high, so it will be able to break this current, small currents. There's no problem with its breaking capacity. The problems here comes with it's the voltage that will develop across contacts when you try to open a capacitive load. Okay, so suppose now at this moment, so when you when the breaker is closed, there will be a small current flowing. Okay, at this moment, I would like to open the breaker. Okay, so when you open the breaker, before you open the voltage now at this shunt capacitance of the line will be at this value. So this is the voltage. This is the voltage that will stay at the capacitor. Okay, at this value it will stay. At the line side, this voltage now it will be at this moment. Once you open the breaker, the voltage across the capacitor will stay same at this value, peak value, negative. However, the voltage of the supply it will continue, right, with this better. So if you take the difference between the voltage at the supply with the voltage stayed at the shunt elements of the line, the voltage difference will be increasing. At this moment, the voltage difference 0. So at this moment, the voltage will be this minus this will be double. Okay. So this is the voltage difference across the contact. So this is the voltage at this moment will be twice times √2 times the phase rated voltage of the grid. That's why the breaker has to handle high voltages under that situations. Okay, and the limiting factor here is this is called now the transient recovery voltage. When you have a capacitance, how the voltage will recover, okay, after you open a breaker. So your limiting factor in this case is not the breaking of a current. The limiting factor here is the voltage. Okay. There is the last things I want to mention: duty cycle. This is the standard operating sequence. So some breaker they are specified as 0.3 CO 3 minute then CO, which means O here means an open, then 0.3 seconds waiting time, between each operation. Then close open, 3 minutes, close open, which means the circuit breaker you can initiate when a fault happens, will open. Then after 0.3 seconds, you can close it and you open it also immediately. Then you have to wait 3 minutes, then you can close and open. This types of sequence required for auto closing circuit breakers intended for rapid auto reclosing. When you trip only one phase and you reclose again. There are other circuit breaker sequence like here, open 3 minutes, then close open 3 minutes. This is not for rapid auto closing because you have to wait. Once you open a breaker, you have to wait 3 minutes. Okay. Then you can close and open. Then you have to wait 3 minutes. Okay. So the circuit breaker rating, they have specified the breaking capacity, they are specified also including the sequence. Yani, there is a short circuit, it's open, you wait 3 minutes, you close during a short circuit and you open, there is 3 minutes wait, you close and open during a short circuit, and that's okay. So this is the sequence. If they can handle this, this is the manufacturer that specify the breaking capacity including the sequence. I'll show inshallah later. There are special requirement for generator circuit breaker. And generator circuit breaker, they have higher X to R ratio. The standard specifies, I told you, 45 millisecond or 17 X to R ratio, while for circuit breaker can go up to 50, specified for circuit breakers, dedicated for generator circuit breakers. It has higher peak withstand capability, 2.7 instead of 2.6 for X to R ratio. This is the peak value, 2.6 times the rated symmetrical rating. They have faster rise of TRVs, and they have delayed current zero. I will show inshallah. For when a fault close to a circuit breakers, there's asymmetrical AC current and DC components. So the fault current will have no zero crossing. For vacuum, for example, for vacuum circuit breaker, it needs to wait the first zero crossing to trip to open its contacts, and that's why there will be a delayed operations for fault clearing, and that's why circuit breaker should handle all of this heat during longer duration of time, and with higher also amount of decaying DC. And circuit breaker dedicated for generator, they have also out of phase switching duty. Yani, because such synchronous generators are synchronized, you might switch while it is not synchronized. So you might switch a breaker out of phase. Okay, so they are rated also for out of phase switching. Unlike distribution circuit breaker, you don't need for synchronization, so there is no need for this specifications. Reclosing duty, there is no, for distribution circuit breaker you need sometimes a recloser, and generators you don't, when there is a fault you open, you don't reclose a generator circuit breaker. So this is not a requirement for generator circuit breakers. They also, generator circuit breaker, they have two breaking capabilities. I'll show you later, inshallah. And so this is like an example of a standard specification from a generator circuit breaker. This is from Siemens circuit breaker. They shows you this is the rated maximum voltage. Inshallah, I want to take a breath, long breath, so that you concentrate with me on this. Now this is a real now breaker, and this is the specifications of this breaker. Rated maximum voltage. هاي تعني شباب. This is like this breaker is 15 kV. ها؟
تايم
ايش تعني؟
السكند
شلون؟
السكند مفروض
السكند
15 ملي سكند.
هاي كيفي شباب. الريتد ماكسيمم فولتج شو يعني في الستان؟ ايش معني هذا؟ هاي السيركت بريكر ريتد 15 كيلو فولت.
يعني السيركت تتحمل 15 كيلو فولت.
I can operate this circuit breaker up to 15 kV. Okay, لكن I can use same 15 kV circuit breaker at 11 kV systems. Okay, but I cannot use circuit breaker 15 kV maximum rated operating voltage for, let's say, higher than 15 kV. So this is the one thing. Now the power frequency they specify 60 Hz for rated continuous current. شنو قلنا rated continuous current شباب؟ Now in this case for this model you can have 1200, 2000, 3000 up to 4000. وش معناته rated continuous current؟ It is the maximum current that the circuit breaker RMS value, of course, the circuit breaker can continuously that can continuously withstand forever. Okay, when it is at a closed position. So this is the rated current of the circuit breakers. Now when I say show circuit breaker, this rated current has to be higher than your full load current. Okay. Now we go to here. I told you about this voltage withstand, rated dielectric strength withstand voltage. Now power frequency, it's 1 minute rating. So although it is 15 kV, but it can handle for 1 minute 38 kV voltage for 1 minute only. If the voltage, it can get damaged if the voltage higher than 38, or you have to do something. If the voltage can go higher than 38 for a duration of 1 minute, you have to do other means to reduce the over voltages, like we use sometimes shunt arresters or high voltage arresters. Okay, there is also impulse rating here, which is in kilovolt peak up to 95 kV. Now if you go to the standard, you will see this power for 15 kV, it is 38 and 95. So if you go to the standard for 15 kV, 15 kV is here, 12 to 15, it is 38 and 95. So that manufacturer, he has adhered to the standard when he specified those values. Okay, Shabab? Now this is the rated short circuit duty cycle, CO, 30-minute CO. So what does that mean?
Close, open.
Yeah,
Then wait
then you
for
have to wait.
Yes.
If you close a breaker, then it trips because of faults. Okay, then you have to wait 30 minutes before you close and open. So this is now, it's okay for generator circuit breakers for because it needs cooling now. It needs time to cool down, then you can close and open again. Okay, but for circuit breaker dedicated for distribution systems, and distribution systems sometimes for overhead lines. If you have overhead lines or transmission systems, sometimes you open one phase, you close it again. So you need, if you have auto closers, then you need shorter time here between opening and closing again. So this is the now this is very important, rated short circuit current. So we have rated short circuit current is 40 kiloampere now. So 40 symmetric. This is the symmetrical current components. We have DC component. What is the percent DC components that is also included in is the rating 75%. Asymmetrical ratio, the S factor here is 1.47. If you apply this formula, you will be able to get, this is the S factor. If you apply now 0.75 square times 2 plus 1 under square root, it will give you 1.4, this value. It will give you this value. So what does that mean? This breaker is designed to handle 45% higher than its breaking capacity to include 75% of a DC current during contact parting time. Asymmetrical, that's why if you multiply this 1.46 times 40K, it will give you this value. This is now the total asymmetrical current that include both AC component and DC components. They have also this transient recovery voltage. Okay. I would like to show you here. This is the standard comparison between IEC, IEEE standard, which is unified. Now we have a unified standard for generator circuit breaker. And both IEC and IEEE, they have same standard. This standard now applies for both IEC, it's common between both IEEE and it used to be different. For generator circuit breaker, they have unified. They call it now dual logo standard. Means it's standard that both IEEE and IEC, they combine together and unify the standard as one. So the short circuit DC time constant is for generators is 133 milliseconds. But for distribution circuit breakers, it is 45 milliseconds. And now, a generator circuit breaker are designed to have a delayed current zero, but it's required. The circuit breaker should handle delayed current zero, while in distributed circuit breaker, no, there is no specifications for circuit breaker capability to handle delayed. There is one thing in generator circuit breakers, they should have two ratings. When the fault at the grid side, we call it generator source. This, when a fault current here, this circuit breaker should handle the current supplied by the generator. We call it now generator source fault. And when the fault's here, at this point, the current will come from the grid to the circuit breaker, and this is called the system source faults. Now, when the fault is here from the system, the fault current is very large, larger than the fault coming from the system. So our breaking capacity mostly is decided based on this for generator, but it has to have also when a fault here where the current is fed from the generator, this current will have high decaying DC, and also the current also AC component also asymmetrical. That's why it will have a delayed zero crossing, and that's why it has to be also rated for this current. That's why we'll have two ratings. In the generator circuit breaker, it has two ratings. system source or generator source rating. We have two ratings, okay? Unlike other circuit breakers. So this is just a comparison between generator circuit breaker and a distribution circuit breakers, okay? For generator circuit breaker, this is the standard duty cycle, where for distribution we could have auto reclosing. That's why we have open 0.3 seconds. Let's take, this is a generator circuit breaker. This is one phase, second, three phase, and this is the, like now it's become a switch gear of a circuit breaker. Now it has a circuit breaker, it have isolate disconnector switch here, we have earth switch, we have so all of this now becomes a switch gear of a generator. And this is what's internal inside the switch gear of the circuit breaker. This is now the vacuum interrupter. This is like the terminal connections of one side. This is the terminal connection of the other side. This is now the earth switch. If you want to ground this from this side, if you want to ground it from the generator side, you will close this. So this bar will short the line, okay, and it will be like connected to ground. Similarly, you have also grounding, which is on the other side of the breakers and so forth. So this is the how a circuit breaker for a generator looks like. This is another specifications for sample of a medium voltage circuit breaker rating, where also they specify rated maximum design voltage, the maximum symmetrical current, the DC components, the short time current rating for 3 seconds, asymmetrical rating, the peak rating, we call it also close and latch rating. This is different. I will not go to this now. I'll give you an examples. Do you have any questions, Shabab? Any questions? So on this circuit breaker also they specify like the interrupting time. ايش معنات interrupting times in cycles 5 cycles؟ ايش معنات interrupting time؟ Circuit breaker operating time. So it is 5 cycle. So it doesn't mean this is the contact parting time. قلنا شنو الcontact parting time for 5 cycles? We go to the standard. I know it is for 5 cycle circuit breakers. Interrupting time will have 3 cycle contact parting time. So the time for the contact to part, okay, is from the receiving a command from the relay. It's until it's physically separate the contacts is 3 cycle. Until fault is clear, it takes 5 cycle. So we can, I can now, this will take you then through example, inshallah. So now to calculate the fault current, now as I told you, fault current have a DC component and AC component, and we call this is asymmetrical current in RMS value. Now the DC value, as a worst case scenario, what will be the DC value? It will be same as the peak of the AC value. So this is the worst case scenario. Decaying DC depends on the moment at which you fault occurs. But the worst case, this value of the DC will be, if we go to the fault current, so this value, the AC value, will be same as it's the peak of the AC component. يعني when it is symmetrical. So this is a worst case scenario to include the maximum DC. So the DC can be defined as the RMS value of the AC, symmetrical value, times root 2 to get S peak. So this is the maximum value of the DC. And it will decay with respect to time at a time constant of tau. And as per standard, I told you tau is 45 milliseconds for most of the breakers, but not for generator breakers. And the time constant, this is defined as L over R or X over omega R, okay? And to get the peak, this is an RMS now. To get the peak, it will the DC value plus the peak of the AC value. So the peak of the AC value is this, okay? This plus the peak of the AC value is AC peak. And if you take now, you can simplify this into root 2 asymmetrical this value. So this is from which I can find, this is what I showed you in the beginning here, to get the peak value of the current. So this is very important to find for close and latch rating. We can also derive the S factor. Where does S factor comes from? If we substitute the DC value plus the symmetrical current value, square under root give you the asymmetrical value, an RMS current. If you take I symmetrical as a common factor here, I'll get this. And this is where the S factor is defined. So this can be also written in different form. So if you divide this over this, I'll get this factor. And this factor is, it can be written in different form. I can take now all of this squared, okay? And I can define now e to the power minus t over tau as percentage DC, so as this. So this is the derivation of the S factor. Let's take an example if you have no questions. So in this example, I have a symmetrical short circuit current, the symmetrical short circuit current rating of a circuit breaker 15 kilo ampere. What does that mean, Shabab? معاي؟ والله تعبتون خلاص.
The symmetrical short circuit current, دكتور.
Okay. هاي manufacturer give us that the circuit breaker can handle this. يعني هذه عبارة عن نفس الريتنج اللي هاي. الحين حاليا we said which is similar to rated short circuit current here, according to American, according to the IEC standards, they specified as symmetrical interrupting current, which is like this. Now we know the circuit breaker is 15K given for you. So this is the symmetrical components, the AC component in RMS value of the fault current at the contact parting time. The circuit breaker can handle this, but the manufacturer already included, in addition to this, additional DC value that can also handle, that can also break. But this is only represent the AC component of the short circuit current at the contact separation time. Now the circuit breaker 5 cycle rated breaker with the minimum contact parting time قلنا 3 cycle. So this is the time for the circuit breaker to open its contacts physically. It's not the time including the arcing time. Including arcing time is 5 cycles. So this is important. I need to know what is the total rated symmetrical current capability of the circuit breaker when the system X to R ratio for during fault does not exceed the standard value of 17 and 60 Hz أو تكون 14 for 50 Hz. طبعا هاي ال 15K is symmetrical component at contact parting time. It's include a decaying DC based on the standard of 17 XR ratio of 45 milliseconds. So السؤال هنا شنو أقصى asymmetrical current that includes ال AC وال DC. هاي ال AC and DC components together at the contact parting time. الجزء الأول. الجزء الثاني, what is the derating factor and the maximum fault current that the circuit breaker can interrupt when applied for systems higher than the standard. الستاندرد قلنا 17 أو 45 milliseconds. الحين استخدمنا XR ratio أعلى. So can I still, this breaker can still break 15 kilo ampere or has to derate it? So السؤال هني أبغي derating factor. الحين هذا بقول بدل ما يكون its ability to break 15 kilo ampere, it will be derated to maybe 11 kilo ampere now because it will be used for a higher X to R ratio. Is the circuit breaker capable to interrupt the maximum steady state short circuit current of 11.5 when X to R rated? X to R is 50. السؤال هنا ثاني, هل هذا السيركت بريكر اللي rated 15 at the standard values of DC current cannot break this current, fault current, when X to R ratio is 50. واضح هالثلاث أسئلة. عندي circuit breakers 5 cycle circuit breaker rated symmetrical current is 15. أبغى أعرف الحين أقصى asymmetrical current اللي المصنع أو manufacturer of this has specified. فأول خطوة قلنا إن نحسب, لازم أعرف شنو الكونتاكت بارتنج تايم اللي هي هنا عاطلنا إياها 3 cycle. ف 3 cycle in times is 3 over, لأن هاي 60 Hz, 3 cycle over 60 cycles, okay, يعطينا 0.05 seconds correspond to 3 cycles. So this is the time until circuit breaker contacts parts separate. Now the standard specified in حق 60 Hz X to R ratio is 17 أو 45 milliseconds. I know this, I can use 45 milliseconds also. And the circuit breaker rating, the circuit breaker rating, symmetrical rating 15 kilo ampere. So how can I have to determine the DC component at 17, at XR 17, a DC component at 17 is at the contact parting time. This is at the standard value, so 0.05 omega over XOR, أو ممكن نقول 0.05 على 45 millisecond. يعني استخدمنا قانون this one. يعني L over R يعني X over R, X على R على أوميجا. هذه هي التاو. والتي هي اللي هي 0.05 اللي هي الكونتاكت بارتنج تايم. I can substitute now directly. This is now what is omega 2 by F. F is 60 Hz. I get now this is 32.9%. When I substitute in the formula as 1 plus 2 times the percentage DC square under the root, I'll get 1.1. So what does that mean, Shabab? That this circuit breaker, manufacturer of this circuit breaker, has rated the symmetrical component, symmetrical current that can break 15 kV, but including DC, it can break at the contact parting 10% more than this. So it is, when you take 10%, means 10% times the symmetrical rating, which is 1.5 plus 15, okay, which will be 16.5 kilo ampere. It's asymmetrical current rating. Okay, so it is 1.1 times symmetrical specified current rating. This what it does mean. Now, second part. Now the DC components, I have to evaluate it at different XR ratio. At part B, what will be the now the rating when I use this circuit breaker for a system that has XR ratio higher than the standard value? Its XR ratio now is 40. So I have to calculate now what will be the DC component as XR ratio, and also I have to find the S factor for XR ratio 40. So substituting also with XR ratio 40 in this formula, still the contact parting time is same, only 3 cycles. They correspond to
Doctor,
0.05.
40 is assumption, right?
Now,
40 is the assumption.
not
Which is
assumption.
X over R. It's more than 70, right? It has to be more
Yeah,
than
احنا
70.
نقول
So
احنا سؤالنا هاي البريكر اللي هو السيمتريكال ريتنج كرنت ريتنج ماله هي 15 كيلو امبير. هاي طبعا محدده لما يكون، لان حسب المانيفاكتشر كلهم خضعوا للستاندرد ان حددوا البريكنج كاباسيتي at contact parting time and when time constant of DC is 45 millisecond او correspond to 17 X to R ratio. حددوا البريكنج capacity. So this is the AC component of the breaking capacity, including a DC components correspond to X to R ratio is 70. Okay, هاي حسب الستاندرد. انا اقول لو احنا الحين استخدمنا السيركت بريكر في in system that has X to R ratio more than 17, I said 40.
okay, it's given.
Okay. هل السيركت بريكر قادر يقطعها ال 15؟ نقول لا، لان الحين بيصير عندنا الدي سي هاير. يعني if I draw the DC component that has higher XR ratio بيصير الديلي، يعني الدي سي ما بينزل بسرعه لو كان نفس 17. 17 اسرع ديكيز، لا 40 بياخذ ديكيز التايم كونستانت اكس تو ار ريشيو اعلى، يعني ال تو ار بتكون اعلى، وبالتالي الدي سي ما بينزل بالسرعه نفس هاي. بالتالي عند لحظه القاطع اللي هو الكونتاكت بارتنج بيكون مقدار الدي سي اعلى من اللي افترض في تصميم هالسيركت بريكر. بالتالي احنا لازم نقلل البريكنج كاباسيتي. يعني I cannot use same انه هو بريكنج كاباسيتي 15 كيلو امبير علشان يتحمل الاديشنال دي سي كومبوننت اللي صارت الحين نتيجه وجود هاير اكس ار ريشيو. فايش قد انا اقدر اقلل هالريتنج الحين نبغى نشوف. اوكي، فاذا حسبنا احنا الاكس ار ريشيو عند الاكس ار، قصدي الاس فاكتور asymmetry فاكتور عند الاكس ار ريشيو 40. بعوضنا الحين نفس الكونتاكت بارتنج تايم بس الاكس ار ريشيو الجديده، فطلعت بدال كان البريكر يتحمل هذا ستاندرد، هاي كان المانيفاكتشر خصص 32% خاصه للدي سي اللي يتحملها بريكر بالاضافه الى الاي سي كرنت. يعني 32% دي سي components بلس الباقي اللي هو بلس 15 كيلو امبير. now الدي سي ما بيصير 32، صار اعلى من 32 سوري، صار الحين 64%. فالاسيمتري فاكتور بدل ما يكون 1.1 صار 1.33. فشلون اطلع الحين يعني هذا الكرنت؟ يعني بيكون الفولت كرنت بيصير عند الكونتاكت بارتنج تايم بتكون اعلى من السيمتريكال كرنت 33%. يعني الدي سي بلس الاي سي بيكون 33% اعلى من الاي سي كومبوننت بروحها. فالحين how do I rate التوتال ريتد كرنت الحين عشان اطلعها؟ نقول الاسيمتريكال ريتنج الجديده اوكي اللي هي الاسيمتريكال ريتنج عند الاكس ار 40 هي 1.33 صح، ضرب السيمتريكال كرنت صحيح. هذه معناتها شنو؟ ان السيمتريكال فاكتور الاس فاكتور ضرب السيمتريكال كرنت يعطيك الاسيمتريكال كرنت. اوكي الاسيمتريكال كرنت اوريدي حددناه in percentage at XR ratio 17. فهي عباره عن asymmetrical current. هذه السيمتريكال كرنت عباره عن الاسيمتريكال كرنت عند الاكس ار ريشيو 17 على الاس فاكتور عند الستاندرد كونديشن عند الريفرنس كونديشن اللي هي عند الاكس ار ريشيو 17. لما تقسمها الاثنين يعطيك السيمتريكال كرنت. فاذا هاي القيمه كم؟ الاس فاكتور عند الريفرنس كونديشن، عند الريفرنس كونديشن اللي هي اكس ار ريشيو كانت 1.1 الاس فاكتور. فاذا بصير 1.33 على 1.11 في السيمتريكال كرنت في الاسيمتريكال كرنت عند الاكس ار 17. معناته ان 1.33 على 1.11 اللي هي بتصير 1.211. معناته وش هاي؟ ان البريكر اللي كان يتحمل اللي صممه يعني ال 15 كي زائد الدي سي عند الاكس ار 17 الحين بتصير لازم اتعداها ب 21% زياده. لو صارت الاكس ار ريشيو 40 الكرنت بيكون بيتعدى الريتنجز هاي عند اكس ار ريشيو ب 1.21 اللي هي 1.33 على 1.1. ونتيجه الهاي بالتالي ان احنا لازم اقلل الحين الريتنج بمقدار 1 على هالقيمه. اوكي اذا I have to reduce the current rating اللي هي ال 15K by a factor of 1.21. فبالتالي لازم البريكنج كاباسيتي الحين بدال ما الحين اتعامل مع ال 15K as breaking capacity او ال be rated to 12.4K علشان يتحمل الإضافة الدي سي الناتجة من إن السيستم XR ratio is 40 higher than the standard value. أوكي. الحين لما أبحث عن short circuit current المفروض ما يتعدل 12.4K AC components بدل مو 15 كيلو أمبير. بارت سي اللاست بارت هنا احنا لو الحين اعطاني شورت سيركت كرنت، قال لي شورت سيركت كرنت اللي بيصير سيمتريكال شورت سيركت كرنت هو 11.5 كيلو امبير. هل البريكر هاي اللي هي ريتد 15 عند ستاندرد ريفرنس فاليو 17 هل قادر يفصل كرنت فوق شورت سيركت كرنت 11.5 كيلو امبير with XR ratio 50؟ ما شباب؟ نروح نفس الشيء اشوف انا عند اكس ار ريشيو كم مقدار السيمتريكال اسيمتري فاكتور وقارنها مع الستاندرد فاليو. اوكي واطلع سيم ثينج فالاسيمتريكال ريتد كرنت اوريدي طلعناها ان تكون اللي هو ات ستاندرد فاليوز كانت 15K ضرب ال 1.1 صح؟ اللي هي من بارت A. 1.1 هو السيمتريكال فاكتور عباره عن 1.1 ضرب السيمتريكال ريتنج اللي هي ال 15K. فالاسيمتريكال كرنت بيكون 1.1 ضرب السيمتريكال كرنت. فبتكون الكرنت معناته اللي بيتحمل البريكر at standard conditions هو 16.5 كيلو اللي هي عباره عن هذه الاي سي زائد الدي سي components in RMS value. اشوف الحين لما عندي 50 اكس ار ريشيو 50 كم بيكون الدي سي؟ نفس الشيء نطلع الدي سي كومبوننت ان برسنتج ونعوضه في المعادله هاي الاس فاكتور عند الاكس ار 50 اللي بتصير 0.68 دي سي برسنتج سكوير. نطلع هذه الفاكتور ونضربه في الشورت سيركت كرنت. اوكي، فبيطلع لي كم لو كان هاي الشورت سيركت كرنت وضربته في وكان اياها دي سي كومبوننت اوكي with XR ratio 50 decaying time constant of that DC is at this rate. فبيطلع لي الكرنت مع الدي سي هو هاي الفاكتور ده ضرب السيمتريكال اي سي كرنت كومبوننت يعطيني 16 بوينت. ونقارن الحين هذا الكرنت اللي هو الاكتوال كرنت مع الدي سي كومبوننت بيكون 16 والبريكنج كاباسيتي اوف سيركت بريكر 16.5 including الدي سي. هل هو يصلح الحين شباب؟
Yes, because the rated is more than the.
Yeah, rated is more than this. So بالتالي الهايل بريكر قادر انه يقطع ال 11.5 kV at a ratio of XR non-standard XR ratio. طبعا احنا ما نحتاج نسوي هالشيء لو كان يعني لو قلنا السؤال الحين is this breaker is capable of breaking 11.5 at standard values of XR ratio 17.
Yes.
Yes, ما يحتاج اشيك. اوكي، لو السؤال لو هالسيركت بريك هل قادر انه يقطع شورت سيركت كرنت اوف 10 كيلو امبير at XR ratio 5 يس بعد، لان at 5 اي شيء اقل من 17 هو بيكون قادر، لانه بيكون الدي سي ايش بيكون اسرع ديكيز، وبالتالي at contact parting time بيكون مقدار الدي سي ايفن اقل من الستاندرد المحسوب في الستاندرد. اوكي شباب، so this is examples. We have many examples I prepared here. You can refer to it. بس في كل الأحوال إحنا لازم نعرف شنو من السيستم. I already علمتكم من قبل إن we need to find first short circuit current اللي هو 3 phase short circuit current at each breaker, right? At each bus. بالتالي هذا نسميه إحنا symmetrical steady state current. ولما نطلع هاي عادة في الكالكوليشن أنا بحسب بس الورست كيس سيناريو لما أمثل كل الاليمنتس باي ذير اندكتنس، يعني أهمل الريزيستنس عشان يكون عندي even higher short circuit current. زين، ومنها بعدين لما أطلع الشورت سيركت كرنت نقارنها مع لازم أعرف الحين في هالسيستم شلون نعرف الإكس آر ريشيو شباب. يعني حق البريكر 4 شنو الاكس تو ار ريشيو حق هالبريكر؟ لازم اشوف من السورس اكس up to this fault point والار ريزيستنس من السورس up to this point ونقسمهم على بعض نقدر نطلع اكس ار ريشيو. اوكي شباب، فور هالبريكر 8 شنو الاكس ار ريشيو؟ نفس الشيء السورس امبيدنس x of the source impedance على ال R of the source impedance. اوكي، هذا البريكر شنو الاكس ار ريشيو؟ هي الامبيدنس من السورس الى هني. هذه الاكس فاليو اوف ات and الار فاليو اوف ات، هاي الاكس ار ريشيو فور ذس بريكر. اوكي شباب. فاحنا علشان نتجنب ان نروح على الكومبلكسيتي، وش يسوون عاده السيركت بريكر ريتنج؟ انا الحين بختار سيركت بريكر هني واعرف الشورت سيركت ليفل هني، اروح مجرد اخذ 25% and 25% higher than this short circuit، وما احتاج احسب الاكس ار ريشيو، اضيف بس 25% higher then short circuit level. بالتالي اختار بعدين symmetrical rating هذه، يعني خلينا نقول طلع الشورت سيركت 10 كيلو امبير، ها 10 كيلو امبير، وابغي اضيف لها 25% عشان اخذ كانه الدي سي، لان الدي سي اتوقع ما بيزيد عن 25% حق ديستريبيوشن بريكرز، مو حق نتكلم عن جنريتور بريكر. جنريتور بريكر الدي سي كومبوننت كان جو هاير ذان higher than 17 الاكس ار ريشيو 17. فنضيف 25% higher than the short circuit current، واختار على طول البريكنج كاباسيتي اللي هي السيمتريكال بريكنج كاباسيتي اللي هي هاي ماكسيموم سيمتريكال انتربتر كيرتنج. فمثلا لو عندي 10 كيلو امبير اضيف له 25% واختار على طول البريكر based on the symmetrical rating، بدون ما نروح الى تقييم ايجاد الاكس ار ريشيو، شوف السيمتريكال فاكتور and so forth. I would like to close here by just showing you ال switch gear components. switch gear components قلنا هو عبارة عن يعني شو الفرق بين السيركت بريكر والسويتش جير؟ نفس ما قلت لكم انه هو السويتش جير عبارة عن عدة components موجودة في one panel. So this different components ممكن يكون الايزوليترز، هاي بيكون عندنا buses، يكون عندنا circuit breaker، عندنا CTs VTs، عندنا earth switches، اوكي، عندنا relays، metering equipments. All of this are integrated in one cabinet and we call it a switch gear. So الهدف من السويتش gear to control, protect and isolate a line, for example, or a generators, or you know, an equipment. Like in this switch gear, this is a generator vacuum GIS, gas insulated switch gear, vacuum interrupter. So this looks like this. So this has a double bus, which is this bus 1, bus 2. It has two disconnector switches, okay, which is the these are the number 1 disconnector switches. This one number 4 and number it has also here the disconnector switches also with the, this is bus bar 1, bus bar 2, with disconnector switches and earth switches integrated here. And they have here we have the circuit breaker, okay. We have the cable will go, this is number 9, the cable end, which is the cable leaving the breaker. So these are the all of this is here inside this. So this is also indoor SF6 now circuit breaker. This is the operating mechanism. That's this is the circuit breakers here. This is the current transformers here. This is the 2 buses, phase bus A, bus B, bus C. So this is the operating the operating and control mechanism. Okay. Here we have the CT, the earth disconnection switches. We have the CTs here. The earth switch operating mechanism is here. Something like this. Okay. If you open these from inside, this is the cable terminals. This is the circuit breaker. عبارة عن 2 parts. This is the CT parts. Now this is a disconnector, which is looks like here. This is the connection, and at the same time, it is an earth switch. So this is at the other end. You have two buses. This is two buses. I can connect this breaker, this line, for example, this line, to either this bus or this bus. So you have two bus system, and at each bus is I have a disconnector, which is this. And this is the circuit breaker, and this is the circuit breaker operating mechanism, which open or close the breakers. We have different standards. We have to refer to most common for circuit breaker IEC IEEE 37 or IEC 62271. These are the commonly used. These are the standards are related to circuit breakers from which I have referred to. With this, I would like to close this chapter. I will send you the slides to see the other examples. And is there any questions, Shabab? And these are the references I have referred to, the standards and some books, some I referred to the manufacturers' data sheets of circuit breakers. So this is a big topic, but I try to do my best to do it in two lectures. But they have one full box on just circuit breaker, Shabab. I'll stop recording if you have no questions.